Hello everyone, this is Yashashvi Srivastava, roll number 18ME31030 of the Department of Mechanical Engineering, IIT Kharagpur, enrolled in its dual degree program in the manufacturing specialization. This is a project on the design and simulation of electro-pneumatic variable valve actuator for a camless engine under the guidance and supervision of Dr. Dhananjay Kumar Srivastava of the Department of Mechanical Engineering as part of my BTP 2. So, we generally make use of a camshaft so as to control our valve opening and closing times. These remain fixed and very often not optimized to the persisting road conditions. Variable valve actuation is a major interest area for research in IC engine, which is aimed to give a greater degree of freedom to optimize the opening and closing timings of the intake and exhaust valves. So what happens is usually the vehicle that comes, it is optimized for a certain speed. However, due to maybe bad roads or maybe extreme traffic conditions, the speed of the vehicle might be less as compared to the optimized speed, and that leads to inefficient combustion. So this is where the variable valve actuation comes in order to take care of this problem. So variable valve actuator systems are divided into two types: the cam-based systems and the camless systems. So now the cam-based systems are further subdivided into three types: the cam switching, cam phasing, and multicam systems. On the other hand, camless systems are subdivided into three types: electrohydraulic, electromagnetic, and electro-pneumatic VVA systems. So this differentiation into hydraulic, magnetic, and pneumatic is based on the principle that is used to control these VVA systems. For principle, or basically whatever is used to control the valve opening and closing. So in hydraulic VVA systems, we make use of fluids which are used to open and close the valves. In magnetic, we use magnetic forces, and in pneumatic, we use air. So the camless VVA strategies and their management systems need to have very good levels of safety and reliability. And for that to happen, they need to be robust. So now we are going to look at the SolidWorks model of the electro-pneumatic variable valve actuator, or the EPVVA, which is the subject of today's project presentation. So this is the assembled and exploded view of the EPVVA. Here we can see the various components of the EPVVA. This is the actual double acting actuator. This is the poppet valve. The poppet valve and the double acting actuator are joined to each other using this brass connector. So this connector can be also made of mild steel, but for this project we use brass. This is the fixture nut. It is used to attach the assembly to a basically rigidly attach the assembly to a surface to carry out the experiments. This is the video of assembly and explosion of the EPVBA. So moving on. Now we are going to discuss the working of the double acting actuator. So the double acting actuator has two chambers, chamber 1 and chamber 2. The chamber 1 is responsible for pushing the valve down. The other hand, chamber 2 is responsible for pushing the valve back up. Each of these chambers have two valves, an inlet and an outlet valve. So what happens is initially The inlet valve for chamber 1 is opened and the outlet valve is closed. And in chamber 2, the outlet valve is open and the inlet valve is closed. So in the inlet valve of chamber 1, compressed air enters the chamber 1 and it pushes the actuator piston downwards. Since there is no resistance from chamber 2, the any air inside chamber 2 is pushed out. Later, the inlet valve of chamber 1 is closed and the outlet valve is opened to the atmosphere. And in the chamber 2, the inlet valve is open and the outlet is closed. So this time the compressed air enters the chamber 2 and that pushes the actuator piston upwards, pushing out the air from chamber 1 into the atmosphere. This is how the actuator piston moves up and down, and hence the poppet valve moves. So now we are going to look at the equations for the mathematical model of the double acting actuator. So on solving the model, we were able to get 6 equations and 6 independent variables. So initially we have x dot equal to v, which is the standard displacement velocity relation. Then we have the mx double dot is equal to p1a1 minus p2a2 minus PATM into AR, which is air rod, minus force of friction. So we get this from the momentum conservation equations. Now here we have P1 dot and P2 dot, which are nothing more than the energy conservation equations for chamber 1 and chamber 2 respectively, and followed by rho1 dot and rho2 dot, which are the mass conservation equations for the two chambers. Solving all these 6 equations together gives us the values of these variables. So in the simulations, we were able to clearly see that the simulated values for the valve lift and the timings for those valve lift, that the highest possible engine speed can be found out from the valve opening and closing times of the EPVVA systems. We observed that higher the valve lift, higher the timings needed to achieve those lifts. So these are the simulation values for valve opening, closing, and dwell in closed position. Now we have plotted these values on a single graph, and the values are 2.5 mm, 5 mm, and 7.5. Thank you.